In this segment, we'll look at the ultimate in simple instruction set architectures and small machine instructions, stack machines. A stack machine dispenses with general purpose registers, replacing them with a stack of numerical values maintained in the CPU on which all mathematical and comparison operations are performed. Importantly, this stack is different from the runtime stack, which is still in memory. Machine instructions do not have register fields in stack machines to specify source operands and a target result. Instead, all machine instructions work with the top values in the stack, and any result of a machine instruction becomes the new top of stack. In stack terms, each operation pops off of the stack its needed operations, as shown here, performs a computation with them, and then pushes back the result. This means almost all machine instructions can be very short, just an opcode, because the operands and target are always at the top of the stack and needn't be specified. This includes even load and store operations, which are operations to and from memory. They are also done onto the top of the stack or from the top of the stack. The great strength of a stack machine is its very short instructions, which are correspondingly fast to load and to execute. Its weakness is that it takes more instructions to get anything done. Can such a limited model really do arbitrary programming operations? Yes. Here's an example stack assembly language, with a summary version of it shown in the notes. The transcript has more detail. It has exactly 9 instructions. It would need several more to be complete, by the way, but these 9 will do for our example. Push pushes a constant onto the stack, and the constant may be any integer, including an address. And in the assembly code, we'll see it can be specified by giving a label in the program. Fetch. This pops the top element off the stack and uses it as an address. It fetches the integer of that address and pushes it onto the stack in place of the address. Put. This one assumes that the top of stack is a value and the next element down is an address. It pops both of them and puts the value at the indicated address. Add, sub, mult, div. These all take the top 2 elements off of the stack and perform the indicated operation on them, leaving the result or pushing the result back onto the top of the stack. The top of the stack is the second operand, and the element below that is treated as the first operand. Go to. Pop the top element off the stack and then just jump to the indicated location. GoNeg is a little more complicated. It assumes the top of stack is a test value and the element below that is the jump location. It pops them both and it jumps if the test value is negative. So how does such a tiny machine language implement, say, the expression x equals a minus b? Well, here's a listing. In this listing, we have a small data segment over here holding x, a, and b, which we'll assume starts at memory address 10,000. In the code, equal x represents the memory address of x as a constant, as it does in ARM assembly. The comments show the contents of the stack from top of stack downward after each instruction, and we'll diagram it as well. So let's walk this code through using the diagram model, which starts with an empty stack in the CPU and the 3 words XAB in memory starting at location 10,000. So instruction 1, push equal x pushes address 10,000 on the stack. Push equal a pushes address 10,004. Fetch pops the 10,004 off the stack and replaces it with the memory content at 10,004, and that's 42, the contents of A. Push equal B pushes the address 10,008. Fetch pops the 10,008 and pushes 10 instead. Now we have stack contents 10, the value of B, 42, the value of A, and 10,000, the location of X. Sub pops the 10 and 42 and replaces them with 42 minus 10, or 32. Remember that the top of stack is the second operand. Finally, put pops the 32 and 10,000 off the stack and writes the 32 at location 10,000. It's all in the planning. For instance, putting the address of X onto the stack first, followed by the values of A and B, meant that the right values would be on the stack for the sub, and then for the put. So question 1, you give it a try. What would be the code for the expression y equals A minus B times C from the transcript? Set up initial data, so A is 42, B is 10, and C is 3. Remember to respect operator precedence and put multiplication first. So here at least is one possible answer, and there really aren't too many different choices, but let's follow this model answer. This code starts by setting up the ultimate target address of Y. Then it pushes the values of A and B and C in that order onto the stack by a sequence of push address and fetch pairs. This leaves B and C at the top of stack, so we can first compute their product via the mult. And this leaves us with the right operands for the sub. Again, the top of stack is the second operand. And then, finally, the put. But does it work with more complex cases? Sure, if you plan it right. Let's try X equals E minus sum of A plus B times sum of C plus 123 minus sum or difference of 42 and D. You're welcome to give it a brief try yourself if you like, although we won't make it an official in-lecture question. So whether you tried it or not, here is an answer. And when you look at this code, you want to shift that over just a little. When you look at this code, you want to read the comments to the side that show the contents of the stack at each step. And I'll leave it to you to read it through carefully and be sure you comprehend it. Take the time to do that, because it'll help you in the next in-lecture question we're going to do. In particular, notice the pattern in this code. It first prepares operands on the stack, and then performs operations on them. And it's recursive. Preparation of each operand may involve a smaller subcomputation, as for instance for the operands A plus B and C plus 123. Also, it pre-stacks operands for lower precedence operations first, to be ready once higher precedence operations have left their result on the top of stack. This pattern is called postfix computation, and there's a corresponding way to write expressions called postfix notation, because it puts the operator after the two operands. The standard notation we routinely use is infix notation, since it puts the operator between the operands. In postfix notation, for example here, A plus B becomes AB plus, and A plus B times C becomes A BC star plus. But the parentheses are just for clarity and are never really needed. We could have just written A B C star plus, because the only way to interpret that postfix expression is to apply the star to the B and the C as operands, and then to apply the plus to the A and the result of BC star. Here are a few more examples to illustrate postfix notation. A minus B minus C, for instance, becomes A B minus C minus. The A and B operation is done first, and then the C is done on the result of it. Or A minus B minus C becomes ABC minus minus. That means that the BC subtraction will be done first, and then the result of that in A will be subtracted. Or A minus 2 minus C times D. A, 2, C, D, and then star, so that the C times D are multiplied first. Then a minus, so that the result of that and 2 are subtracted. And finally a minus, subtracting all of that from A. Or A minus B minus C times 2. A, B, C minus, thus the B and the C are subtracted. The result of that is multiplied by 2, and then all of that subtracted from A. Or A minus B minus C. A, B subtracted, then C subtracted from that, times 2, put on a 2 and subtract, or multiply the result by 2. Or if you like, A minus B minus C times 2. A, B, C minus minus, as we had before, but then add the 2 star to multiply all that by 2. Hopefully that gives you an idea of the pattern at least. Using those examples as a model, translate the following infix expression into postfix, please. That's question number 2, by the way. So the answers here are A times B, AB times, and then 42 times D, 42D times, and then a subtract of those two. And then finally an E subtracted from the result. Or AB star, 42D star, and the E immediately subtracted from the 42 times D, and finally all that subtracted from A times B. Or A times B, well, all of this stuff really, B 42DE, so we get the D minus E, and then the 42 multiplied by the result of D minus E, and the B and all of that subtracted, and then finally the entire result of that parenthesized structure multiplied by A. And finally the A times B minus 42 times D minus E, the B and the 42 are subtracted first, right inside here, and that result multiplied by A. All of that then multiplied by D, and then finally all of that with E subtracted. Okay, now try it the other way, translating these postfix notations back into infix, please. You'll need parentheses in several cases, but don't add them unless necessary. Okay, and the answer for that is the following. Here, for instance, C minus D is a unit, and we need to parenthesize because it's going to be multiplied by B, which otherwise would have higher precedence. And the grand total of that is subtracted from A. Here, A and B are a unit, A minus B, and then multiplied by C, and then finally with D subtracted. Over here, B and C minus is a unit, multiplied by A, and then with D subtracted. And then finally, last but not least, A plus B is a unit, C plus 123 is a unit, those two multiplied, then subtracted from E, and finally 42 and D subtracted, and that subtracted from the original first part of the expression. Okay, so infix and postfix. Now, going back to our stack machine here, what about loops, ifs, and other control structures? How do they work? The goTo and goNeg branch instructions turn out to be all we need if we plan correctly. So let's try writing some stack machine code for the loop shown here in the transcript while I is less than or equal to 42, I equals I plus 1. And that would be as shown here and in the transcript. So track it through and see how it works by following the stack contents here. And in particular, notice that we are pushing 42 and the value of I, doing a subtract, and then doing a negative, go negative, if the result of that subtraction is less than 0, causing it to jump past the loop. Reason about the code, and then answer the question, what would change to that in that code if the tester instead I is greater than or equal to 42? The answer is you need to swap around the I and the 42. We would check, go past the loop if I minus 42 is less than 0 instead. Reversing the roles of 42 and I by switching their order results in a test for I greater than or equal to 42 instead of less than or equal to. Now, you might reasonably wonder if a single conditional instruction, GoNeg, can cover all possible comparisons. It appears to be capable of only less than or equal to tests by checking whether a preceding subtraction had a negative result, and apparently also for greater than or equal to tests by reversing the operands. But in fact, all 6 comparisons can be rephrased with some complexity as logical combinations of just less than comparisons. And here's a little chart showing how that works. A less than B, of course, translates to A less than B. A greater than B translates to B less than A. A less than or equal to B translates to not A greater than B. A not equal to B translates into either A less than B or B less than A. Fill in the 2 remaining lines here as question 5. The answer is A greater than or equal to B is not B greater than A. And A equal to B is the negation of the A not equal to B case. Now we've seen in earlier code that logical and or, and not can be implemented by appropriate combinations of branches. So the GoNeg instruction can deal with arbitrary comparisons in logic. In practice, a stack machine would have more types of comparison instructions to keep code from being needlessly complex. But it's useful to see that less than, in principle at least, is all you need. Okay, we've now seen 3 major design philosophies for ISAs: CISC, RISC, and stack machine. If they were gasoline engines, CISC would be a 1970s V8, powerful but dated. RISC would be a modern, efficient 4-cylinder, and stack machines would be 1-cylinder small engines for special applications like, say, lawnmowers. Practical stack machines include very small processors for controlling devices and other specialized applications. And they also include software virtual machines. The Java VM is a notable example. And finally, it's worth a brief note that Hewlett-Packard calculators understand postfix notation and can be operated that way. HP uses the alternate term RPN, standing for reverse Polish notation, to describe postfix, but it's the same concept. If you can wrap your mind around it, postfix notation is more efficient than infix because it requires no parentheses, so highly technical users sometimes prefer it.